Now we're going to generalize what we know in one dimension to two dimensions. The definitions of position, velocity, and acceleration are the same, except that now we have to worry about both x and y components. The position of a particle with respect to a reference point is indicated by its position vector r. If this reference point is our origin, you can see that r vector points from the origin to the position, to the location of the particle, and it has components x and y. So the position vector is given as xi hat plus yj hat in terms of the unit vectors I hat and j hat on the x and y axis respectively. The displacement vector delta r of such a particle is the difference between its final and initial position vectors. If the particle changes position, it goes from point A to point B, you can see that there is a change in the position vector, so final position vector minus initial position vector rb minus ra will give us the displacement vector delta r. So these are both measured in meters. The average velocity will be the displacement divided by the time interval to complete the displacement. So it is rv minus ra vectors divided by the time interval tb minus ta. So tb is our arrival time at point B, and ta is the time of departure from point A. And you can see that this V average and the displacement vector are functions of RB and RA, so they're independent of the path taken, they only depend on the initial and final positions. The instantaneous velocity will be the limit as delta t goes to 0, delta r over delta t, which is by definition the derivative of the position vector with respect to time. And if we look at its magnitude, it will be a scalar quantity which we call speed. Now the average acceleration is the change in velocity per unit time, v final minus v initial divided by delta t. So on xy plane, you can see that we go from initial position ri to final position rf with an initial velocity vi and final velocity vf. So if we subtract from vi, we obtain delta v, and delta v vector divided by the delta t, the time it takes to complete this motion, is average acceleration. On the other hand, if you look at the limit as delta t goes to delta v over delta t, it is dv dt. So as I said, everything is the same as in one-dimensional motion, but here we have to worry about x and y components separately in order to solve two-dimensional motion problems. And also we have the speed, that is the magnitude of the instantaneous velocity, that's defined this way. So we don't talk about the average speed given in terms of the total distance traveled per time here, but we could also define that as well. As I said, everything is the same except that we have to worry about x and y components. Okay, now to digest what we have learned from these kinematics equations, let's take a look at a few examples. Our first example is related to a particle motion along the x-axis. A particle moves along the x-axis. Its position is given by the equation x equals 2 plus 3t minus 4t squared, with x in meters and t in seconds, so they're in SI units. Determine its position when it changes direction, and so we're going to look for the time when it changes direction and its velocity when it returns to the position it had at t equals to 0. Okay, so what I have to note here is that when I reach the point it changes direction, that means it's going to start moving back. Therefore, the position x will be a maximum. So for part A, I note that at the point it changes direction x is a maximum. So its position will be maximum. And note that this is a one-dimensional motion because we're moving on the x-axis. Now, if x is a maximum, I know x of t was given as 2 plus 3t minus 4t squared, 2 plus 3t minus 4t squared, x as a function of time. So if I know position as a function of time, when the position is a maximum, that means the instantaneous velocity at that point will be 0. It will be changing direction. So that's an extremum point in the function x of t. So I have to take the derivative of 2 plus 3t minus 4t squared with respect to time. So that will give me 3 minus 8t. And the velocity will be equal to 0 at t is equal to 3 over 8 seconds. So what is this maximum position? That's the question. We have to determine its position when it changes direction. So what is the value of x when t is equal to 3 over 8 seconds? It is 2 plus 3t, so it is 3 times 3 over 8, minus 4t squared, minus 4 times 9 over 64. So this will give us 2 plus 9 over 8 minus 9 over 16, because we will have this 4 reducing 64 to 16. So this will be 16. So here we have 2 plus 18 minus 9 over 16. If we have a common denominator here, we multiply the second term by 2, top and bottom by 2. So we're going to obtain 2 plus 9 over 16, which is roughly 2.56 meters. So this will be our maximum distance from the origin, 2.56 meters. And once again, I note here that velocity at t is equal to 3 over 8 seconds must be equal to 0. It changes direction. Okay. Now part B, we need to know its velocity when it returns to its position it had at t equals 0. So what is the position at t is equal to 0? So let's determine that. At t is equal to 0, if I substitute t equals to 0 for 2 plus 3 times 0 minus 4, 0 square, I obtain 2 meters. So the position was 2 meters. Then at time t final time, I'm going to have again a position of 2 meters when it returns. So the question is, when does that happen? So let's take a look. X at t final is 2 plus 3t final minus 4t final square. This is going to be equal to 2, the original position. So that means I have 3t final minus 4t final square is equal to 0. So this will give me t final times 3 minus 4t final equals to 0. I know that t final cannot be equal to 0 seconds. This is not possible because that's t initial. So here I have t final must be equal to 3 over 4 seconds. So my question is, what is its velocity when it returns to its original position? If I look at velocity Vx, it is the derivative of position with respect to time, dx dt, which I have found in part A to be 3 minus 8t, and I want to know the final value of the velocity at t equals t final. So it is 3 minus 8 times 3 over 4. So this 4 will make this 8 2. So it is 3 minus 6, and therefore Vx at t final will be minus 3 meters per second. Note that I'm careful about putting the units for my answer. This is very important because we are reporting a number here. Okay, so to summarize, we've looked at an example for a one-dimensional motion where we know the position as a function of time. We wanted to determine its position when it changes direction, and a particle will change its direction when its velocity is 0, or the position will reach an extremum for the one-dimensional motion, and its velocity when it returns back to its original position. I've looked for an extremum in the position by taking the derivative with respect to time, setting it equal to 0. I found that the extremum occurs at t is equal to 3 over 8 seconds, and the position at t equals 3 over 8 seconds I have found to be 2.56 meters. Then I wanted to determine its original position at t is equal to 0. It was 2 meters. Then apparently it's returning back to its original position. When does it return back to its original position? X at t final will be equal to x at t equals 0, which is 2 meters. That gives me 3 over 4 seconds. When I take the derivative of the position with respect to time, 3 minus 8t, and evaluate it at the time of return, 3 over 4 seconds, I find the velocity, the final velocity, to be minus 3 meters per second when it returns to its original position. Now let's look at another example. A particle moves in the xy plane starting from the origin at t equals 0 with an initial velocity having an x component of 20 meters per second and a y component of minus 15 meters per second. So clearly this is two-dimensional motion. The particle experiences an acceleration in the x direction given by 4.0 meters per second square. Determine the velocity vector at any time, calculate the velocity and speed of the particle at t equals 5 seconds, and the angle the velocity vector makes with the x-axis, determine the x and y coordinates of the particle at any time t and its position vector at this time. So we know that at t is equal to 0, it has an x component of its velocity to be 20 meters per second and a y component of its velocity to be minus 15 meters per second. Its position at t is equal to 0. Do we know? We do, because it's starting from the origin. So its position at t equals 0 is 0 I hat plus 0 j hat in meters. And its acceleration, there is an acceleration on the x-axis. Ax is 4.0 meters per second square. There is no acceleration on the y-axis. So ay is then 0 meters per second square. Okay, so what is its velocity vector at any time t? So let's start with this. We are trying to determine its velocity vector at any time t. Now, since we have a y is equal to 0, the y component of its initial velocity, minus 15.0 meters per second, is a constant of the motion, and dvy dt, which would be ay, is 0. There is no change in time. Ax, on the other hand, is dvx dt. It is 4 in I hat direction, so it's 4 meters per second because I have shown it as ax. So from time t equals 0 to t, if I take the integral of dvx, I have integral from 0 to t 4 dt. So this will give me a delta vx of 4t. So if I write this as a vector, delta vx vector is 4t I hat. Okay, so vx at time t minus vx at time t equals to 0 is 4t I hat, so written as a vector here. Then I see that my vx vector will be at the initial velocity 20.0 I hat plus 4t I hat meters per second. Since Vy is not changing, then I can write the velocity vector as a function of time. The velocity vector is 20.0 plus 4.0 t I hat minus 15.0 j hat meters per second. Considering x and y components separately, I can form my total velocity vector. Part B. Now I want to know the velocity and speed at t equals 5.0 and the angle with the x-axis. Now if I know velocity is a function of time, I can just evaluate it at t is equal to 5.0 seconds. So that will give me 20.0 plus 4 times 5 I hat minus 15.0 j hat, and this will give me meters per second. So this will give me, for the velocity at t is equal to 5.0 seconds, 40 I hat minus 15 j hat meters per second. And now the speed at t is equal to 5 seconds, the speed at t is equal to 5.0 seconds is the magnitude of the velocity at t is equal to 5.0 seconds. And what is the magnitude at t is equal to 5.0 seconds? It's the square root of 40 square plus 15 square. So I find that the magnitude is, at t is equal to 5.0 seconds, about 42.7 meters per second. So this is the speed of the particle at that time. Now the angle the velocity vector makes with the x-axis can be found by taking the dot product with I hat. It's the magnitude of velocity vector, the magnitude of I hat 1, and cosine theta with respect to x-axis. So this is 40 I hat minus 15 j hat dot product with I hat, and the magnitude is 42.7. So 42.7 cosine theta x is equal to 40, because I hat dot I hat is 1, I hat dot j hat is 0. So here I have theta x is equal to cosine inverse of 40 divided by 42.7. So this gives me an answer for theta x plus or minus 20.5 degrees. Now I know that the velocity Vx is, x component is positive, y component So because it's 40 I hat, y component is negative, x component positive, y component negative, corresponds to fourth quadrant. So if I'm in the fourth quadrant, that means I need to take the angle theta x to be minus 20.5 degrees, not plus, because if I take plus, Vx and Vy would be positive. All right. Now, part C, determine the x and y coordinates of the particle at any time t and position vector. So let's work on the position vector. Now the velocity vector, we know velocity at any time t is derivative of position vector with respect to time, dr dt. Then we find that the displacement delta r is integral from 0 to t v of t dt. So this will be the integral from 0 to t 20.0 plus 4.0 t I hat minus 15 j hat, our velocity vector dt. So we find that the displacement delta r will be 20.0 t minus plus 2.0 t square I hat minus 15t j hat. So this is basically x of t I hat plus y of t j hat, since the position at t equals to 0 is 0. So because delta r vector will be equal to r at time t minus r at t equals to 0 is delta r vector, which is r at time t, and r at t equals 0 is 0. We start from the origin. Therefore, we find that the x component, x of t, is 20.0 t plus 2.0 t squared. And the y component will be y of t, that's the coefficient of j hat, is minus 15 t. So these are both in meters, and therefore I find that in meters, the position vector is 20.0 t plus 2.0 t squared I hat minus 15.0 t j hat in meters, and t is in seconds. Okay, so this is 15.0. Okay, so to summarize, we have an example for two-dimensional motion where we have an initial velocity with an x and y component, x component positive 20 meters per second, y component minus 15 meters per second, under a constant acceleration of 4 meters per second square on the x-axis. There's no y acceleration. We want to know velocity and position as a function of time, and at a particular time we want to know the velocity and speed and the angle with the x-axis. So what I have done is basically use the relationship between acceleration and velocity. Acceleration is dv dt for instantaneous acceleration. Since a y is 0, y component is a constant of the motion, x component integral over time from 0 to t gives me the change in the velocity vector. So I find the velocity vector as a function of time to be 20 plus 4t I hat minus 15 j hat. If you put t equals 0 here, you obtain the initial velocity. Then we evaluate that t equals 5 seconds. We take the dot product with I hat to find the angle it makes with the x-axis. When I look at the magnitude of the velocity vector at that point, I find its speed. And since I know that the velocity vector at that point has a positive x component and negative y component, it's in the fourth quadrant, I choose the angle minus 20.5 degrees with respect to the x-axis to be in the fourth quadrant. Then I look at the relationship between velocity and position vector, and the change in the position vector, the displacement, is integral over time of velocity dt. And since the original position is origin, the initial position is origin, I can determine r as a function of t, and the coefficient of I hat gives me the x component, coefficient of j hat gives me the y component. Now let's move on to another example. Two objects A and B are connected by hinges to a rigid rod that has a length L. The objects slide along perpendicular guide rails as shown in the figure. Assume object A slides to the left with a constant speed v. So you can see they are connected. The object A is moving with a constant speed v towards the origin on the x-axis, and B can only move on the y-axis. Find the velocity of object B as a function of angle theta. Describe VB relative to V. Is VB always smaller, larger, or the same as V? Does it have some other relationship? So let's start with part A. So first I want to note the position of the object A as a function of time. So how can I determine position of object A as a function of time? Well, so here you can see we have a distance x from the origin, and we're moving with constant velocity v towards the left. So it is basically x minus vt. So we have a constant velocity to the left, x minus vt. At t equals 0, this is x, and as time goes by, x will be decreasing with a constant velocity v, so this will be x minus vt. And from the geometry here, you can also see that from ABO triangle or OAB triangle, the length L of this rigid rod that connects objects A and B has a projection onto the position of A, which is L cosine theta. So this is equal to L cosine theta, where theta is changing as a function of time, and what is happening as A approaches the origin, theta will be increasing, right? So it will be an increasing function of time. On the other hand, I want to look at the position of B as a function of time. Well, you can see that B is going to be related to L as well. It will be L sine theta. So it's going to be L sine theta of t. I don't know what its velocity is. This is what I would like to determine. So if I look at the rate of change of position of A with respect to time, dxa dt, it is, as you can see here, minus v, because it's moving in minus I hat direction. And it is also a function of angle, and angle is a function of time. So I can also write this as dxa dt, dt, d theta, d theta, dt. So dxa d theta, d theta, dt. It's a function of a function. Okay, so dxa dt, d theta, so cosine theta has a derivative minus sine theta, so this will be minus L sine theta, and d theta dt will be here. So this is velocity of A. And at the same time, when I look at the rate of change of position of B with respect to time, dy b dt, which is what I'm trying to determine. It is also a function of angle dyb d theta dt, which is the derivative of L sine theta with respect to theta is L cosine theta d theta dt. So this is velocity of B. Now, if I take the ratio VB to VA ratio, what do I find? It is VB divided by minus V, which is VB is L cosine theta d theta dt, and VA is minus L sine theta d theta dt. So d theta dt's will cancel, and also we're going to get rid of these L's, and this minus sign will become a plus. And we find that velocity of B, of object B, is V times cosine theta over sine theta, which is cotangent theta. So VB is V times cotangent theta. Now let's move on to part B. Describe VB relative to V. Is VB always smaller, larger, or same as V, or does it have some other relationship? Well, let's analyze this answer. When theta is equal to 0 degrees, we have cosine 0 over sine 0, which is 1 over 0, positive infinity. And on the other hand, when theta is equal to 90 degrees, we have VB equals V times cosine 90 over sine 90, which is 0. And on the other hand, when is VB equal to V? When cotangent theta is equal to 1, or theta is equal to 45 degrees. So the conclusion is that for theta less than 45 degrees, between 0 and 45 degrees, VB is greater than V. When theta is exactly equal to 45 degrees, VB is equal to V. And when theta is greater than 45 degrees, 45 to 90 degrees, we're going to find that VB is less than V. Actually, VB becomes 0 when theta is equal to 90 degrees. So we find this relationship between VB and V as a function of angle theta. Okay, now to summarize, we're looking at two objects connected by a rigid rod, and we're looking at assuming that the object A moves on the x-axis, is bound to move on the x-axis, and object B is bound to move on the y-axis. They're moving, sliding along perpendicular rails. And object A is moving with constant velocity v to the left. We want to know the velocity of VB as a function of angle theta and relationship between VB and V. For that, I have determined the position of A with as a function of time. It is from the geometry L cosine theta as a function of time, which is x minus vt if I call the position at t equals 0x, and yb is L sine theta of t. By taking the derivative with respect to time, I determine va, which is minus v. By taking the derivative with respect to time of yb, I determine the velocity of b. So this is basically what is labeled as VB in the problem. And this is VA. So if I take the ratio of VB to VA, I see it's VB divided by minus V, which is L cosine theta d theta dt, divided by minus L sine theta d theta dt. L's and d theta dt's cancel, and I find that VB is related to V with a factor of cotangent theta. And when theta equals 0, the ratio is infinite, so VB will be very, very high. When theta equals 90, VB will be 0. And when theta equals 45 degrees, VB is equal to V.